let's get started. Sorry for the excitement and consequent delay. I'd like to begin today with a quote from Malthus. Malthus is a famous classical economist whose most important work is related to, well, this quote, in fact. So he was interested in population dynamics and the effects of the increases in population on the allocation of resources. So I'll read what Malthus has to say about this. I think I may fairly make two postulata. First, that food is necessary to the existence of man. Secondly, that the passion between the sexes is necessary and will remain nearly in its present state. Assuming then my postulata is granted, I say that the power of population is indefinitely greater than the power in the earth to produce subsistence for man. So that's a statement of the Malthusian hypothesis. The idea is a simple one, and you can probably get it from the quote there. Let's imagine that time proceeds along this sort of axis, and that population is going to increase at an exponential rate. That's essentially what Malthus is presuming. And so in that case, we'll have something like population following an exponential path over time. And he has an idea which is spelled out more explicitly in his essays on population, that the progress of agriculture was his main concern. His idea was that you can see improvements in agriculture, but those improvements were most likely to increase at a linear rate. And so anytime you have an exponential racing something that's linear or even polynomial, the exponential is eventually going to win. And so if something like this is the Malthusian hypothesis, that eventually population, with exponential population growth, will have to outstrip his concern, again, was mostly food, but other resources, other natural resources or other kind of resources would be included there as well. Okay, so I want to spend today talking a little bit about present value. We're going to be talking about time today, so we're going to be sort of in an explicitly dynamic world. It's going to allow us to consider questions related to these. I'm going to start with a little generalization of present value, where we sort of finished last time, and then we'll talk about the problem facing a firm that's trying to extract resources over time, when it's could be oil or something like the examples we've given previously. And we'll sort of finish up with a return to some Neo-Malthusian thinking and spend just a little bit of time on that. Okay, so that's the agenda. I guess just one administrative item. Problem set 8 is available on bSpace. We brought some printed copies. We haven't had a chance to download those, but not as we haven't printed as many as usual, so let me go ahead and pass these around. If you've already downloaded it or printed it out, don't take one, and that way there'll be enough for everyone. Conversely, if you're at the back of the room and the problem sets are gone before they get to you, please just download it off bSpace. Okay. All right, questions before we begin? All right, let's get started then. So I want to remind you, we were talking last time about the present value of flows of resources, and I'd gone ahead and worked out giving expressions for the present value of things like a perpetuity. So you'll recall that a perpetuity is an asset that yields a fixed quantity of resources every period. So you can go, you can buy a perpetuity for yourself if you like, and it'll yield some number of dollars every year forever. And so we talked about how to value those things. I hadn't, I think, gotten around to giving a general expression for present value in the more general case where the flow might change over time. So in the case of a perpetuity, you get the same dollar amount every year. In the more general case, you might get different dollar amounts in different years, and so I want to consider that now. Here's a general expression. So the general expression for the present value of an asset that gives a quantity yt in period t, where you have face constant interest rates r, is given by this infinite sum. So let me just relate. So this is, again, a general expression for this. So the present value of an asset that yields these payouts yt different periods is given by that. Let me just relate this to the perpetuity. Since this is a general expression, it ought to be true for this one as well. For the case of a perpetuity, we have v equal to the sum, and we're going to do this from t equal 1 to plus infinity. And the expression we have up there is 1 over 1 plus r all raised to the t times yt. Now what's the case? What's special about a perpetuity is that yt is equal to some constant y bar. The payoff doesn't change over periods. The whole point of a perpetuity is you get the same amount every year no matter what. Yes, Eric. Let me observe that let me do it this way. 1 over 1 plus r to the t is equal to 1 over 1 plus r t. Yeah. Okay. Thanks for the question. I'm glad to have cleared out that possible confusion. So this expression is the same as this because we just have a 1 in the numerator. All right, so in this case, this perpetuity is special because the yt is constant, and so as a consequence, in the general case, this yt shows up in every term of this infinite sum, and we can't factor it out. For the perpetuity, though, since it doesn't depend on t, we can. So for a perpetuity, we have v equal to just y, because we can factor it out of this thing, times the sum t equal 1 to infinity 1 over 1 plus r to the t. And let me go ahead. Did I work this out last time? I think I did. So for the case of a perpetuity, here with t equal to 1, we have this constant y. We've got this infinite sum. Now, I gave an expression last time for the value of a slightly different infinite sum. I said that if we had something like alpha to the t equals 0 to plus infinity, so notice this is t equal to 0, this is t equal to 1, and we had the absolute value of alpha less than 1, then this thing was equal to 1 plus r over r. I'm sorry. I said it's equal to 1 over 1 minus alpha, and in this case, that implies that the sum t equals 0 to infinity of 1 over 1 plus r to the t would be equal to 1 plus r over r. Okay, is that clear? Should I go over the steps there? I'm not sure. I sort of think that was unclear, in fact. Let me try to fix that. So here's the general rule. Provided that alpha is less than 1 absolute value, the infinite sum from t equals 0 to infinity is given by this expression. So this is the general case. In this case, I'm going to apply it to this case. And so using this and taking alpha equal to 1 over 1 plus r, I get this expression. So this is a useful thing to know. To get the value of this perpetuity, I got 1 times this infinite sum, which is almost this, but not quite. What's different? Yeah, the value of t starts from 1 here. It starts from 0 here. But I can convert between those things just by multiplying by a factor of 1 over 1 plus r. So the sum of t equal 1, the infinite sum t equal 1 to infinity of 1 over 1 plus r is equal to y times 1 over 1 plus r, the infinite sum t equals 0 to infinity 1 over 1 plus r to the t. So I'm factoring out one of my 1 plus r terms from this infinite sum, so this has to be equal to this. Is that clear? This is just algebra, but if you're not familiar with the infinite, or it's not comfortable with infinite sums, it may look a little funny. Anyway, so then this is equal to y times 1 over 1 plus r. And now we can substitute in this, for this expression, we know this is equal to 1 plus r over r. So this is 1 plus r over r. And so this whole thing is just equal to y over r. So this is the value of perpetuity when we start the payments, in t equal 1. So that's a pretty nice expression. We take the constant payoff we get, we divide by the interest rate, and that tells us the value of this infinite sum. All right, so quick question. Is a perpetuity more valuable when r is high or when r is low? When r is low. So why? What's the intuition for that? We can see that from the formula. If r is a big number, like 10%, like 0.1, then we just get the present value is 10 times the value of y. But if r is a small value, like say 1%, then the value of this perpetuity is 100 times r. Right, so what's the intuition for what's going on there? Yes? Okay, so why is it worth less and less? Yeah, so let me be clear. So the inflation doesn't play any role here. And it's true, it could play a role. These are nominal interest rates. So if r was 10% and it's a nominal interest rate, and let's say it was all inflation, then that's going to be part of the reason why the value of the perpetuity is small, because you're dividing by 10% instead of 1%. So this is a nominal rate. So inflation can play a role, but even if it's not inflation, if real interest rates are 10% versus 1%, how should we think about this? Yeah.
Your opportunity cost is higher because you could invest in something else.
Yeah, no, that's exactly the answer I'm looking for. So the value of r tells you the opportunity cost of those funds. So instead of investing in a perpetuity, if interest rates are high, you can put your money in some other investment, and it would yield returns of 10%. So we'll think about the value of this perpetuity depends on the opportunity cost of the original investment, and that's exactly captured by the interest rate. Okay. All right. So this is a general expression for the present value of a perpetuity. It works out to be this. For any asset, we can use this expression. So if we don't have a perpetuity, but instead some asset that gives payoffs that are different in different periods, we can still use this more general expression. Okay, let me give you an example of an investment along those lines. So let's think about the possibility of investing in a solar panel. So not a financial investment. Let's instead think about an investment that a homeowner might make to reduce their heating bills. So we'll think about investing in photovoltaic cells to put on your roof to reduce your heating or electricity bills. This is a particularly relevant example here in Berkeley because Berkeley is in 2008 launched an initiative which they called the FIRST program. So their idea was that they wanted to encourage the placement of photovoltaic cells on the roofs of houses, and they were concerned that households in Berkeley might not do so because of difficulties in obtaining financing. So there's a considerable upfront cost associated with installing a substantial number of solar cells on top of your roof, and so most people might not want to use cash for that. And so the idea behind the city program is that the city would offer financing to help cover that. Okay, so let's think about that program for a moment. I'm going to come up with some numbers that are estimates that you can get if you go to this web page. They give some estimates toward the bottom here and they give you there's an evaluation here. I'm sorry, that's not what I want. Oh, here it is. The Smart Solar Analysis here gives some estimates of costs and benefits associated with the photovoltaic cell installation. So I'm going to throw out some of those numbers. So let's think about investing in photovoltaic cells on your roof. So some estimates of a reasonable sized installation of those for a typical Berkeley house calls for an investment up front in the neighborhood of $30,000. So for 30 grand, you can put in I think it's 150 square feet of photovoltaic cells, and that's enough to produce meaningful quantities of electricity. So this is something that's going to happen at time equal to 0. So I'm going to use a little t to indicate the time. In the very first period, before you realize any savings from the program, you have to make this upfront investment. Okay. At later periods, there's also the maintenance cost. So one thing you need to do if you have a solar cell installation is go up there and clean it off periodically, get the leaves off, scrub off any dirt that's accumulated, or else the efficiency of the thing goes down considerably. So an estimate of the maintenance cost is on the order of $150 per year. You might need to replace cells now and then, I suppose. So anyway, this is an estimate of that cost, though. And for an installation, for the size installation you get for $30,000, the estimated savings over the course of a year from that size installation are on the order of $600 per year. Okay, so you save $600 in electricity or heating bills. You have to spend $150 in annual maintenance. So that's net savings of $450 per year, which sounds great, but that's offset by the need to make this initial investment of 30 grand. Okay, so is that clear here? Okay. All right. So let's think about under what conditions it would make sense to make this sort of investment. So we've got a setup here where we're assuming a maintenance cost of $150 a year, which doesn't change over time. We're assuming that's constant over the lifetime of the program. We're assuming savings of $600 a year, and again, we're not assuming that this changes over time. That may or may not be a good assumption, but we're making it here the way I've written this. So how would we go about computing the present value of the savings from this program? How could we proceed? Yes. Yeah. So we'll assume right now it's forever. Good question. Yeah. So very good. So this is like a perpetuity. We're saying you're going to get $450 net per year forever, and we're going to time that starting at this t equals 0. You make the investment. You get payoffs starting from t equal to 1. So use the formula for perpetuity. And what we find is that the value of the investment will be equal to $450 divided by the interest rate. Okay, so now the question is, the question that should face a homeowner is whether or not the value of this is greater than or equal to the cost of this thing. And the cost here, we've already factored in the annual maintenance cost. The only remaining cost you have to worry about is this 30 grand for the initial investment. So is this value greater than or equal to $30,000? And what will that depend on? This depends on the interest rate. So if interest rates are high, that will be less likely to be true. because the opportunity cost of $30,000 today will be large. You could take that 30 grand and invest it in some asset that yielded an interest rate of R. So if R is high enough, that's going to tend to exceed the payoffs of $450 you get from investing in this thing. So we can go ahead and ask the question. So this thing implies that or hinges on whether R is greater than or equal to exactly 1.5%. That's what this ratio of 450 to 30 grand would be. Right? This is equal to 450 divided by $30,000. Is that calculation clear? All right. Now, so for this to be a worthwhile investment, this is the question. And if R is larger than 1.5%, it's not a good investment from the standpoint of the homeowner. If it's less than 1.5, it is. Now, the actual costs of this program, the financing that we talked about that the city of Berkeley offered on this program was to set R equal to, so the Berkeley First program set R equal to the rate on a U.S. Treasury with a 10-year maturity. So those are numbers we've examined fairly recently. This rate plus 3.5%. So we can go back in our notes from last lecture or perhaps the lecture before and see what the current return on a 10-year T-bill is. But since we're adding 3.5 to that positive number, for sure the interest rate that the homeowner pays is going to be more than 1.5%. Yes?
Would it be possible to get sort of an estimation of interest rates at a time and then put that in the model?
Yeah, so one shortcoming of this, that's a great question. One shortcoming of this is that we're assuming that R doesn't change over time. I mean, there's much of stuff we're holding fixed over time. One is we're saying the maintenance costs aren't going to change, the benefits aren't going to change. That's maybe plausible. We're also assuming that R is fixed over time, and that's, we've seen recently. I showed you a graph last time of different yield curves. There's been big changes in this number in recent years. So there's two ways to answer that. First, if we knew what future interest rates were going to be, we could take care of that using a formula, or I guess a slight modification of a formula I gave a couple lectures ago. So if we knew that interest rates were going to be in the future, we could change this formula. Let me look at here. I wonder where this is yet. We could change this formula so that if we had varying interest rates, then our formula would look like that. But the general formula, present value formula would be the sum t equal, how am I doing this one? 1 to infinity. And but instead of this 1 over 1 plus r to the t, we have the product of, say, s equal 1 to t of 1 over 1 plus rt. So this would be the generalization of that if we knew what future interest rates were going to be and if they varied over time. I think I got that right. Oh, I need to put in my yt still, of course. So this, if rt is constant over time, this turns into the early expression. Yes, Hillary? So that's right. So this is the arrangement we've set up here. The decision I've talked about making for the homeowner here is strictly a financial decision. We're asking whether the savings the homeowner receives from the program exceeds the present value. The present value of the savings exceeds the initial cost. That's the question. And so it's certainly true that if by investing in these solar panels you reduce greenhouse gas emissions and that had a value, that calculation isn't entering here. You should bear in mind. I mean, no. The short answer to your question is no. There's no externalities considered here. If you were going to do this calculation and you cared about greenhouse gases, another thing you might want to think about is the cost of buying a permit, an abatement. And so I think a ton of carbon dioxide right now goes for around $13. You can pay somebody else to emit that much less. So something like that is the cost of reducing CO2 emissions. So another question you should ask, I don't know the answer to this off the top of my head, is whether or not investing in the solar panels would be an efficient way to reduce CO2 emissions or not. Okay, we'll come back to that. We'll come back to externalities next week, though. Okay. Okay, I want to say one more thing about this program. So so we talked about the possibility of interest rates varying. So I'm going to set that aside. We're going to assume that interest rates are constant. But let's suppose that y is not constant, but that it takes a certain known value. So what I want to do now is assume that you get $450 in savings for a while, but that after 20 years the solar cells wear out or something. That the value of the investment terminates at 20 years out. So what we have, so let's say there's a finite life. There's a finite life to the payoffs. And so how can we think? We've got a general expression for the present value of this thing up there. How should we think about the YTs if your PV investment falls apart in 20 years? We've got two cases to consider. You've got savings from the program if you're less than 20 years out, and you've got savings from the program if you're more than 20 years out. So this is equal to 450 if t is less than or equal to 20, and 0 if t is greater than 20. Okay, so this is a simple. You can imagine much more complicated kinds of variation in YT